Nice to see you again. In today's video, I'll be covering some questions related to Case Study 5, Helicopter Racing League, and Case Study 6, EHR Healthcare. I'll also be covering some questions related to the Mount Kirk Games case study. Without further ado, let's get started. Company Overview. Helicopter Racing League, HRL, is a global sports league for competitive helicopter racing. Each year, HRL holds the World Championship and several regional league competitions where teams compete to earn a spot in the World Championship. HRL offers a paid service to stream the races all over the world with live telemetry and predictions throughout each race. Solution Concept. HRL wants to migrate their existing service to a new platform to expand their use of managed AL and ML services to facilitate race predictions. Additionally, as new fans engage with the sport, particularly in emerging regions, they want to move the serving of their content, both real-time and recorded, closer to their users. Existing technical environment. HRL is a public cloud-first company. The core of their mission-critical applications runs on their current public cloud provider. Video recording and editing is performed at the racetracks, and the content is encoded and transcoded, where needed, in the cloud. Enterprise-grade connectivity and local compute is provided by truck-mounted mobile data centers. Their race prediction services are hosted exclusively on their existing public cloud provider. Their existing technical environment is as follows. Existing content is stored in an object storage service on their existing public cloud provider. Video encoding and transcoding is performed on VMs created for each job. Race predictions are performed using TensorFlow running on VMs in the current public cloud provider. Business requirements. HRL's owners want to expand their predictive capabilities and reduce latency for their viewers in emerging markets. Their requirements are: support ability to expose the predictive models to partners, increase predictive capabilities during and before races, race results, mechanical failures, crowd sentiment, increase telemetry and create additional insights, measure fan engagement with new predictions, enhance global availability and quality of the broadcasts, increase the number of concurrent viewers, minimize operational complexity, ensure compliance with regulations, create a merchandising revenue stream. Technical requirements. Maintain or increase prediction throughput and accuracy, reduce viewer latency, increase transcoding performance, create real-time analytics of viewer consumption patterns and engagement, create a data mart to enable processing of large volumes of race data. Executive Statement. Our CEO, S. Hawk, wants to bring high-adrenaline racing to fans all around the world. We listen to our fans, and they want enhanced video streams that include predictions of events within the race, e.g., overtaking. Our current platform allows us to predict race outcomes but lacks the facility to support real-time predictions during races and the capacity to process season-long results. Okay, this is all the background information related to Case Study 5 Helicopter Racing League. Let's start with the related questions of this case study. Question 188. For this question, refer to the Helicopter Racing League HRL case study. Your team is in charge of creating a payment card data vault for card numbers used to bill tens of thousands of viewers, merchandise consumers, and season ticket holders. You need to implement a custom card tokenization service that meets the following requirements. Asterisk, it must provide low latency at minimal cost. Asterisk, it must be able to identify duplicate credit cards and must not store plaintext card numbers. Asterisk, it should support annual key rotation. Which storage approach should you adopt for your tokenization service? Store the card data in Secret Manager after running a query to identify duplicates. B. Encrypt the card data with a deterministic algorithm and store it in Firestore using data store mode. C. Encrypt the card data with a deterministic algorithm and shard it across multiple memory store instances. D. Use column-level encryption to store the data in Cloud SQL. Okay, this question from the Helicopter Racing League case study is about designing a secure and efficient storage system for a credit card tokenization service. We need a solution that is fast, cheap, can find duplicate card numbers without storing the actual numbers, and supports key rotation. The most important technical requirement here is the need to identify duplicate credit cards without storing them in plaintext. This means we need to use a special kind of encryption called deterministic encryption, where the same input always produces the same encrypted output. This allows us to check for duplicates by comparing the encrypted values. With that in mind, let's look at our options. Let's start with option A, using Secret Manager. This is incorrect. Secret Manager is for storing a small number of high-value secrets, like a single API key. It's not a database designed to handle and query tens of thousands of customer records. Next, option C suggests using Memory Store. While Memory Store is very fast, it's an in-memory cache and is generally a more expensive option for persistent storage compared to other databases, which conflicts with the minimal cost requirement. Option D suggests using column-level encryption in Cloud SQL. While possible, standard database encryption is usually not deterministic for security. Also, a relational database like Cloud SQL can be less scalable and more costly for this type of simple key-value workload than a NoSQL alternative. This brings us to option B, which is the correct answer. This solution uses Firestore in data store mode, which is a scalable, low-latency, and cost-effective NoSQL database. Crucially, it specifies using a deterministic encryption algorithm. This allows the service to check for duplicate cards by comparing the encrypted data, which satisfies the key requirement. This combination provides a secure, scalable, and cost-effective solution. Therefore, the storage approach you should adopt is B. Encrypt the card data with a deterministic algorithm and store it in Firestore using data store mode. Question 189. For this question, refer to the Helicopter Racing League HRL case study. Recently, HRL started a new regional racing league in Cape Town, South Africa. In an effort to give customers in Cape Town a better user experience, HRL has partnered with the content delivery network provider, Fastly. HRL needs to allow traffic coming from all of the Fastly IP address ranges into their virtual private cloud network, VPC network. You are a member of the HRL security team, and you need to configure the update that will allow only the Fastly IP address ranges through the external HTTPS load balancer. Which command should you use? A, B, C, and D are shown in the provided image. Okay, this question from the Helicopter Racing League case study is about network security. The goal is to allow traffic from a specific partner, the CDN provider Fastly, to reach our application through a Google Cloud external HTTPS load balancer, while blocking other traffic. The key to this question is knowing the correct security service to use with an external load balancer. For this, you need to use Cloud Armor, which allows you to create security policies. VPC firewall rules, on the other hand, apply to virtual machines within your network, not the load balancer itself. With that in mind, let's evaluate our options. Let's look at options B and C. Both of these are incorrect because they use the Cloud Compute Firewall Rules command. As we just discussed, VPC firewall rules are the wrong tool for protecting an external HTTPS load balancer. Now let's look at option A. It correctly uses the Cloud Compute Security Policies command for Cloud Armor, but its source is src IP ranges *. This would allow traffic from any IP address on the internet, which is not what we want. We only want to allow traffic from Fastly. This brings us to option D, which is the correct solution. It uses the correct Cloud Compute Security Policies command. Most importantly, it uses a special expression that calls a pre-configured function. Evaluate pre-configured expr, sourceplist Fastly. This is a built-in Cloud Armor feature that automatically uses Google's managed list of all of Fastly's IP addresses. The command then sets the action to allow. This is the most efficient and secure way to whitelist traffic from a known CDN provider like Fastly. Therefore, the correct command you should use is D. Question 190. For this question, refer to the Helicopter Racing League HRL case study. The HRL development team releases a new version of their predictive capability application every Tuesday evening at 3 a.m. Universal Time coordinated to a repository. The security team at HRL has developed an in-house penetration test cloud function called Airwolf. The security team wants to run Airwolf against the predictive capability application as soon as it is released every Tuesday. You need to set up Airwolf to run at the recurring weekly cadence. What should you do? A. Set up cloud tasks and a cloud storage bucket that triggers a cloud function. B. Set up a cloud logging sync and a cloud storage bucket that triggers a cloud function. C. Configure the deployment job to notify a pub/sub queue that triggers a cloud function. D. Set up identity and access management, IAM, and confidential computing to trigger a cloud function. Okay, this question from the Helicopter Racing League case study is about setting up an automated security test. The key requirement is that the security test, which is a cloud function, needs to run as soon as the main application is released every Tuesday. This points to an event-driven architecture. Instead of running the test at a fixed time, we want the release event itself to trigger our security test function. This ensures the test always runs immediately after the new code is deployed. With that in mind, let's look at our options. Let's start with option A, using cloud tasks and a cloud storage trigger. This is not the best fit. While a file being uploaded to cloud storage can be an event, it's not the most direct way to signal that a new application version has been deployed. Option B, using a cloud logging sync, is also incorrect. A logging sync is for routing log entries, not for signaling the completion of a deployment pipeline. Option D is incorrect as well. IAM and confidential computing are security services and are not used for triggering functions based on events. This brings us to option C, which describes the correct, event-driven, and loosely coupled architecture. The deployment job, after it successfully releases the new version of the application, would publish a simple message to a cloud pub/sub queue. The Airwolf cloud function would be configured to listen to this specific queue. As soon as the message arrives, the function is triggered instantly, and the penetration test begins. This is a reliable and highly scalable way to chain automated processes together. Therefore, the best way to set this up is C. Configure the deployment job to notify a pub/sub queue that triggers a cloud function. Question 191. For this question, refer to the Helicopter Racing League HRL case study. HRL wants better prediction accuracy from their ML prediction models. They want you to use Google's AI platform so HRL can understand and interpret the predictions. What should you do? A. Use explainable AI. B. Use Vision AI. C. Use Google Cloud's Operations Suite. D. Use Jupyter Notebooks. Okay, this question from the Helicopter Racing League case study is about a key area of machine learning called interpretability or explainability. The goal is not just to get a prediction from a model, but to understand why the model made that specific prediction. With that in mind, let's look at our options. Let's start with option B, Vision AI. This is a powerful service for image analysis, but it's a pre-built tool. It's not the feature you would use to understand and interpret your own custom-built models. Next, option C is Google Cloud's Operations Suite. This is incorrect because the suite of tools, which includes monitoring and logging, is for observing the operational health of your application, like its CPU usage or error rates. It doesn't provide insights into the model's decision-making process. Option D suggests using Jupyter Notebooks. While notebooks are the primary environment for developing and training models, they are not the specific feature of the AI platform that provides explanations for predictions from a deployed model. That is a distinct, managed feature. This brings us to option A, which is the correct answer. Explainable AI is the specific feature set within Google's AI platform designed to provide interpretability for your models. When you request a prediction from a model with explainable AI enabled, it can also give you feature attributions, which tell you how much each piece of input data contributed to the final result. This directly helps you to understand and interpret the model's predictions. Therefore, the correct thing to do is A. Use explainable AI. Question 192. For this question, refer to the Helicopter Racing League HRL case study. HRL is looking for a cost-effective approach for storing their race data such as telemetry. They want to keep all historical records, train models using only the previous season's data, and plan for data growth in terms of volume and information collected. You need to propose a data solution, considering HRL business requirements and the goals expressed by CEOs. Hawk, what should you do? Use Firestore for its scalable and flexible document-based database. Use collections to aggregate race data by season and event. B. Use Cloud Spanner for its scalability and ability to version schemas with zero downtime. Split race data using season as a primary key. C. Use BigQuery for its scalability and ability to add columns to a schema. Partition race data based on season. D. Use Cloud SQL for its ability to automatically manage storage increases and compatibility with MySQL. Use separate database instances for each season. Okay, this question from the Helicopter Racing League case study is about choosing the right long-term storage solution for a large and growing dataset. The key requirements are that it needs to be cost-effective, handle massive scale, and, most importantly, allow for efficiently training machine learning models on just the data from the previous season. With that in mind, let's look at our options. Let's start with the options that suggest transactional databases, which are A, B, and D. Firestore, Cloud Spanner, and Cloud SQL are all powerful databases, but they are designed for live application workloads, not for storing and analyzing huge historical datasets for machine learning. For this kind of large-scale analytics, you need a data warehouse. This brings us to option C, which is the correct answer. This solution uses BigQuery, which is Google's serverless data warehouse, built for cost-effective storage and fast analysis of massive datasets. It addresses all the requirements perfectly. Its ability to easily add new columns handles the future growth in information collected. Most importantly, the strategy to partition race data based on season is the key to both performance and cost-effectiveness. When the data science team needs to train a model on the previous season's data, they can write a query that only scans that specific season's partition. This is incredibly fast and cheap because BigQuery doesn't have to look at all the other years of historical data. Therefore, the best data solution is C. Use BigQuery for its scalability and ability to add columns to a schema, and partition race data based on season. Question 193. For this question, refer to the Helicopter Racing League HRL case study. A recent finance audit of cloud infrastructure noted an exceptionally high number of compute engine instances are allocated to do video encoding and transcoding. You suspect that these virtual machines are zombie machines that were not deleted after their workloads completed. You need to quickly get a list of which VM instances are idle. What should you do? A log into each compute engine instance and collect disk, CPU, memory, and network usage statistics for analysis. B. Use the Cloud Compute Instances list to list the virtual machine instances that have the idle true label set. C. Use the Cloud Recommender command to list the idle virtual machine instances. D. From the Google console, identify which compute engine instances in the managed instance groups are no longer responding to health check probes. Okay, this question from the Helicopter Racing League case study is about a common cost optimization task, finding and dealing with idle or zombie virtual machines. The key requirement is to find a quick way to get a list of these idle instances. With that in mind, let's look at our options. Let's start with option A, which suggests logging into each machine manually to collect statistics. This is incorrect because it's the exact opposite of a quick solution. This would be an incredibly slow and manual process. Next, option B suggests listing VMs that have an idle true label. This is also incorrect because Google Cloud does not automatically apply such a label. You would first need another tool to identify the idle VMs before you could even apply this label, so it doesn't solve the problem. Option D suggests looking for instances that are failing health checks. This is incorrect because a VM can be idle, meaning it has very low CPU usage, while still being perfectly healthy and responding to health checks. This method would find broken VMs, not idle ones. This brings us to option C, which is the correct and Google-recommended solution. Google Cloud has a built-in service called Recommender, which includes an idle VM recommender. This tool automatically analyzes the CPU and network usage of your instances and uses machine learning to identify which ones have been idle. You can then quickly get this list of recommended instances to delete or shut down by using the Cloud Recommender command or by looking in the GCP console. This is the fastest and most automated way to solve the problem. Therefore, the best thing to do is C. Use the Cloud Recommender command to list the idle virtual machine instances. Let's go to Case Study 6 EHR Healthcare Content. Company Overview. HR Healthcare is a leading provider of electronic health record software to the medical industry. EHR Healthcare provides their software as a service to multinational medical offices, hospitals, and insurance providers. Solution concept. Due to rapid changes in the healthcare and insurance industry, EHR Healthcare's business has been growing exponentially year over year. They need to be able to scale their environment, adapt their disaster recovery plan, and roll out new continuous deployment capabilities to update their software at a fast pace. Google Cloud has been chosen to replace their current colocation facilities. Existing technical environment. HR software is currently hosted in multiple colocation facilities. The lease on one of the data centers is about to expire. Customer-facing applications are web-based, and many have recently been containerized to run on a group of Kubernetes clusters. Data is stored in a mixture of relational and NoSQL databases, MySQL, MS SQL Server, Redis, and MongoDB. HR is hosting several legacy file and API-based integrations with insurance providers on premises. These systems are scheduled to be replaced over the next several years. There is no plan to upgrade or move these systems at the current time. Users are managed via Microsoft Active Directory. Monitoring is currently being done via various open-source tools. Alerts are sent via email and are often ignored. Business requirements. Onboard new insurance providers as quickly as possible. Provide a minimum 99.9% availability for all customer-facing systems. Provide centralized visibility and proactive action on system performance and usage. Increase ability to provide insights into healthcare trends. Reduce latency to all customers. Maintain regulatory compliance. Decrease infrastructure administration costs. Make predictions and generate reports on industry trends based on provider data. Technical requirements. Maintain legacy interfaces to insurance providers with connectivity to both on-premises systems and cloud providers. Provide a consistent way to manage customer-facing applications that are container-based. Provide a secure and high-performance connection between on-premises systems and Google Cloud. Provide consistent logging, log retention, monitoring, and alerting capabilities. Maintain and manage multiple container-based environments. Dynamically scale and provision new environments. Create interfaces to ingest and process data from new providers. Executive statement. Our on-premises strategy has worked for years but has required a major investment of time and money in training our team on distinctly different systems, managing similar but separate environments, and responding to outages. Many of these outages have been a result of misconfigured systems, inadequate capacity to manage spikes in traffic, and inconsistent monitoring practices. We want to use Google Cloud to leverage a scalable, resilient platform that can span multiple environments seamlessly and provide a consistent and stable user experience that positions us for future growth. That's all the background information of Case Study 6, EHR Healthcare. Now let's move on to the questions related to this case study. Question 194. For this question, refer to the EHR Healthcare case study. You are responsible for ensuring that EHR's use of Google Cloud will pass an upcoming privacy compliance audit. What should you do? Choose 2. Verify EHR's product usage against the list of compliant products on the Google Cloud compliance page. B. Advise EHR to execute a Business Associate Agreement (BAA) with Google Cloud. C. Use Firebase authentication for EHR's user-facing applications. D. Implement Prometheus to detect and prevent security breaches on EHR's web-based applications. E. Use GKE private clusters for all Kubernetes workloads. Okay, this question from the EHR Healthcare case study is about ensuring privacy compliance, which in the context of healthcare almost always refers to HIPAA. There are 2 foundational, non-negotiable steps that any healthcare organization must take before they can be considered compliant on Google Cloud. With that in mind, let's evaluate the options. First, let's look at the incorrect options. C, D, and E all suggest specific technical implementations like using Firebase authentication, Prometheus, or GKE private clusters. While these can be good security practices, they are not the fundamental mandatory requirements for passing a privacy audit. They are implementation choices not foundational compliance steps. This brings us to the two correct answers. Let's look at option B. To be compliant with HIPAA, a healthcare organization must execute a Business Associate Agreement, or BAA, with Google Cloud. This is a legal contract that outlines the responsibilities of both parties regarding the protection of health information. Without this agreement in place, you are not compliant. The other correct answer is option A. The BAA does not cover every single service that Google Cloud offers. Google maintains a specific list of services that are covered under its HIPAA BAA. Therefore, a critical step in any audit is to verify that your application is only using products from this officially compliant list to handle any sensitive patient data. Therefore, the two things you must do are A and B. Question 195. For this question, refer to the EHR healthcare case study. You need to define the technical architecture for securely deploying workloads to Google Cloud. You also need to ensure that only verified containers are deployed using Google Cloud services. What should you do? Choose 2. A. Enable binary authorization on GKE and sign containers as part of a CI/CD pipeline. B. Configure Jenkins to utilize credes to cryptographically sign a container as part of a CI/CD pipeline. C. Configure Container Registry to only allow trusted service accounts to create and deploy containers from the registry. D. Configure Container Registry to use vulnerability scanning to confirm that there are no vulnerabilities before deploying the workload. Okay, this question from the EHR healthcare case study is about securing the software supply chain for your containers. The goal is to create a system that guarantees that only trusted, verified container images are allowed to run in your Google Kubernetes engine environment. This requires both a way to verify the images and a way to enforce the policy that only verified images can be deployed. With that in mind, let's look at our options. Let's look at option C. This is about controlling which service accounts can push images to your registry. While this is an important part of security, it doesn't verify the actual content of the image, so it's not a complete solution. A trusted service account could still accidentally push a vulnerable image. Option B describes a very specific implementation of the signing process using Jenkins and credes. While this is a valid way to sign an image, let's first consider the more fundamental components of the solution. Now let's look at option D. This suggests using vulnerability scanning in Container Registry to confirm there are no vulnerabilities. This is a critical verification step. Before you can say an image is verified, you must scan it for known security issues. So this is a key part of the solution. Option A describes the complete enforcement framework. It talks about enabling binary authorization on GKE, which is the gatekeeper that blocks unverified deployments. It also mentions the need to sign containers as part of a CI/CD pipeline. This signature is the proof that an image has passed all the required checks, such as the vulnerability scan mentioned in option D. The combination of performing a vulnerability scan and then having a system like binary authorization enforce that only scanned and signed images can be deployed creates a complete and secure process. Therefore, the two actions that together create the required secure architecture are A and D. Question 196. You need to upgrade the EHR connection to comply with their requirements. The new connection design must support business-critical needs and meet the same network and security policy requirements. What should you do? A. Add a new dedicated interconnect connection. B. Upgrade the bandwidth on the dedicated interconnect connection to 100G. C. Add 3 new cloud VPN connections. D. Add a new carrier peering connection. Okay, this question is about upgrading a network connection for a business-critical healthcare application. The key phrase here is business-critical, which in the cloud world is a strong signal that you need a highly available and redundant solution. For a network connection to be highly available, you need at least 2 separate paths. If one path fails, traffic can automatically switch to the other, ensuring your application stays online. Simply making a single connection faster doesn't make it more reliable. With that in mind, let's look at our options. Let's look at option B, which suggests upgrading the bandwidth of the existing connection. This is incorrect because it only makes the single connection faster. It doesn't add any redundancy. If that one link goes down, you still have an outage. Next, option C suggests adding cloud VPN connections. While VPNs can be part of a high availability strategy, usually as a backup to a primary connection, dedicated interconnect is a much higher performance and more reliable solution suitable for a business-critical primary link. Option D, adding a carrier peering connection, is a type of interconnect, but the core requirement for high availability is having a second, redundant path, which is more clearly stated in option A. This brings us to option A, which is the correct and Google-recommended solution. To create a highly available business-critical connection, you add a second, new dedicated interconnect connection. By having two independent physical connections, you create a redundant setup. If one of the interconnects fails, traffic can be routed through the other, ensuring that your application remains connected and available. Therefore, the correct thing to do is A. Add a new dedicated interconnect connection. Question 197. For this question, refer to the EHR healthcare case study. You need to define the technical architecture for hybrid connectivity between EHR's on-premises systems and Google Cloud. You want to follow Google's recommended practices for production-level applications. Considering the EHR healthcare business and technical requirements, what should you do? Configure two partner interconnect connections in one metro, city, and make sure the interconnect connections are placed in different metro zones. B. Configure two VPN connections from on-premises to Google Cloud, and make sure the VPN devices on-premises are in separate racks. C. Configure direct peering between EHR Healthcare and Google Cloud, and make sure you are peering at least two Google locations. D. Configure two dedicated interconnect connections in one metro, city, and two connections in another metro, and make sure the interconnect connections are placed in different metro zones. Okay, this question from the EHR healthcare case study is about designing a highly available and production-ready network connection between an on-premise data center and Google Cloud. The key is to follow Google's recommended best practices for business-critical applications. For a truly production-grade, business-critical connection, Google recommends a topology that can survive not just the failure of a single network link, but the failure of an entire physical location or metropolitan area. This is the 99.99% availability design. With that in mind, let's look at our options. Let's start with option B, which suggests using Cloud VPN. This is not the best choice for a primary, production-level connection because VPN runs over the public internet and doesn't offer the guaranteed performance and reliability of a dedicated link. Next, option C suggests direct peering. This is incorrect because direct peering is for connecting to Google's public services, not for creating a private connection to your VPC for your applications. Option A is a good start, but it's not the complete, recommended solution for the highest availability. Having two connections in one city protects you if one of those connections fails, but it doesn't help you if there's a major problem, like a natural disaster, that affects the entire city. This brings us to option D, which is the correct answer and describes Google's recommended topology for 99.99% availability. This architecture provides the maximum level of redundancy. You set up two connections in one metropolitan area, and then you set up another two connections in a second, geographically separate metropolitan area. This protects you from a single link failure, a single location failure, and even the failure of an entire city, ensuring your critical application remains connected. Therefore, the best practice you should follow is D. Configure two dedicated interconnect connections in one metro, city, and two connections in another metro, and make sure the interconnect connections are placed in different metro zones. Question 198. For this question, refer to the EHR healthcare case study. You are a developer on the EHR customer portal team. Your team recently migrated the customer portal application to Google Cloud. The load has increased on the application servers, and now the application is logging many timeout errors. You recently incorporated pub/sub into the application architecture, and the application is not logging any pub/sub publishing errors. You want to improve publishing latency. What should you do? Increase the pub/sub total timeout retry value. B. Move from a pub/sub subscriber pull model to a push model. C. Turn off pub/sub message batching. D. Create a backup pub/sub message queue. Okay, this question from the EHR healthcare case study is about optimizing the performance of cloud pub/sub. The specific goal is to improve or reduce the publishing latency, which is the time it takes for a single message to be sent from the application to the pub/sub service. With that in mind, let's look at our options. Let's start with option A, which suggests increasing the retry timeout. This is incorrect. A retry timeout is for handling errors, but the question states that the application is not logging any publishing errors, so this is not the root cause of the latency. Next, option B suggests changing the subscriber model from pull to push. This is also incorrect because it relates to how messages are received from pub/sub. Our problem is on the other side, about how messages are sent to pub/sub. Option D, creating a backup queue, is a pattern used for reliability and handling failed messages. It has no effect on the latency of the initial message publishing. This brings us to option C, which is the correct answer. By default, the pub/sub client libraries use a feature called message batching to improve overall efficiency. This means the library will collect several messages together for a very short period and send them all in one API call. While this is great for throughput, it adds a small, intentional delay to each individual message while it waits for the batch to fill. If your top priority is to reduce the latency of every single message, you can turn off pub/sub message batching. This forces the library to send each message immediately, which will improve the publishing latency. Therefore, the correct thing to do to improve publishing latency is C, turn off pub/sub message batching. Question 199. For this question, refer to the EHR healthcare case study. In the past, configuration errors put public IP addresses on back-end servers that should not have been accessible from the internet. You need to ensure that no one can put external IP addresses on back-end compute engine instances and that external IP addresses can only be configured on front-end compute engine instances. What should you do? Create an organizational policy with a constraint to allow external IP addresses only on the front-end compute engine instances. B. Revoke the compute.network admin role from all users in the project with front-end instances. C. Create an identity and access management IAM policy that maps the IT staff to the compute.network admin role for the organization. D. Create a custom identity and access management IAM role named GCE_frontend with the compute.addresses.create permission. Okay, this question from the EHR healthcare case study is about creating a strong security guardrail. The goal is to enforce a rule that says backend servers can never have public IP addresses, while still allowing front-end servers to have them. This requires a tool that controls what can be configured, not just who can configure it. With that in mind, let's look at our options. Let's start by looking at the options that focus on IAM, which are B, C, and D. These are all incorrect because IAM is the wrong tool for this specific problem. IAM is about granting permissions to users. It controls who can perform an action. It cannot be used to enforce a rule like, this specific type of VM is not allowed to have an external IP. That is a policy constraint, not a permission. Option C would actually make the problem worse by granting a powerful role. Option B is too broad and might remove permissions that people need. And option D, creating a custom IAM role, can't solve this because you can't create an IAM permission that is conditional on a resources configuration in this way. This brings us to option A, which is the correct solution. The Google Cloud service designed for this is the Organization Policy Service. It allows you to set specific constraints on your resources. There is a constraint called compute.vm external IP access that does exactly what's needed. You can create a policy to deny external IPs for all VMs in a project, and then create a more specific policy that allows it only for your designated front-end instances. This enforces the rule at the platform level, regardless of who is trying to create the VM. Therefore, the correct thing to do is create an organizational policy with a constraint to allow external IP addresses only on the front-end compute engine instances. Question 200. For this question, refer to the EHR healthcare case study. You are responsible for designing the Google Cloud Network architecture for Google Kubernetes Engine. You want to follow Google best practices. Considering the EHR healthcare business and technical requirements, what should you do to reduce the attack surface? Use a private cluster with a private endpoint with master authorized networks configured. B. Use a public cluster with firewall rules and virtual private cloud VPC routes. C. Use a private cluster with a public endpoint with master authorized networks configured. D. Use a public cluster with master authorized networks enabled and firewall rules. Okay, this question from the EHR healthcare case study is about designing the most secure network architecture for a Google Kubernetes Engine, or GKE cluster. The main goal is to reduce the attack surface, which means minimizing how many components of our cluster are exposed to the public internet. With that in mind, let's look at our options. Let's start by looking at the options that suggest using a public cluster, which are B and D. A public cluster, by definition, means your worker nodes can have public IP addresses. This immediately creates a larger attack surface than a private cluster, where nodes only have internal IPs. So, for the highest level of security, we can rule these options out. Now let's compare the two private cluster options, A and C. Option C suggests using a private cluster but with a public endpoint for the control plane. While this is better than a fully public cluster, it still exposes your cluster's API server to the public internet, which is a significant security risk that we want to avoid. This brings us to option A, which is the correct and most secure configuration. This architecture uses multiple layers of security. First, a private cluster ensures the worker nodes do not have public IPs. Second, a private endpoint ensures the cluster's control plane, or API server, also does not have a public IP, making it completely inaccessible from the internet. Finally, Master Authorized Networks acts as an additional firewall, allowing you to specify exactly which internal IP ranges are allowed to talk to the control plane. This is the most secure design and does the most to reduce the attack surface. Therefore, the best thing to do is use a private cluster with a private endpoint with Master Authorized Networks configured. Question 201. You have been engaged by your client to lead the migration of their application infrastructure to GCP. One of their current problems is that the on-premises high-performance SAN is requiring frequent and expensive upgrades to keep up with the variety of workloads that are identified as follows: 20 terabytes of log archives retained for legal reasons, 500 gigabytes of VM boot/data volumes and templates, 500 gigabytes of image thumbnails, 200 gigabytes of customer session state data that allows customers to restart sessions even if offline for several days. Which of the following best reflects your recommendations for a cost-effective storage allocation? A. Local SSD for customer session state data. Lifecycle managed cloud storage for log archives, thumbnails, and VM boot/data volumes. B. Memcake backed by Cloud Data Store for the customer session state data. Lifecycle managed cloud storage for log archives, thumbnails, and VM boot/data volumes. C. Memcake backed by Cloud SQL for customer session state data. Assorted local SSD-backed instances for VM boot/data volumes. Cloud storage for log archives and thumbnails. D. Memcake backed by persistent disk SSD storage for customer session state data. Assorted local SSD-backed instances for VM boot/data volumes. Cloud storage for log archives and thumbnails. Okay, this is a storage architecture question. We have 4 different types of data, and we need to choose the most cost-effective Google Cloud storage solution for each one. Let's analyze the workloads first. We have log archives, VM data, image thumbnails, and customer session state. For the first 3 logs, VM templates, and thumbnails, these are all essentially files that can be stored as objects. The most cost-effective and scalable place for this is Google Cloud Storage, ideally with a lifecycle policy to move the log archives to a cheaper storage class over time. The most complex requirement is the customer session state. It needs to be fast, but also persistent for several days. Option A suggests using local SSD, which is incorrect because local SSD is ephemeral and the data would be lost if the VM restarts. Options C and D also have flaws, either using ephemeral storage for VM boot volumes or suggesting a complex setup of backing a cache with a raw disk. This brings us to option B, which provides the best solution for all workloads. For the session state, It recommends a standard high-performance pattern, using a fast in-memory cache like Memcake for quick access, backed by a durable and persistent database like Cloud Data Store. This ensures both speed and that the data is not lost. For all the other data types, the log archives, the image thumbnails, and the VM templates and inactive volumes, it correctly recommends using lifecycle-managed cloud storage, which is the most cost-effective and scalable solution. Therefore, the recommendation that best reflects a cost-effective storage allocation is B. Memcake backed by Cloud Data Store for the customer session state data. Lifecycle-managed cloud storage for log archives, thumbnails, and VM boot/data volumes. Question 202. Your BigQuery project has several users. For audit purposes, you need to see how many queries each user ran in the last month. What should you do? A. Connect Google Data Studio to BigQuery. Create a dimension for the users and a metric for the amount of queries per user. B. In the BigQuery interface, execute a query on the jobs table to get the required information. C. Use BQShow to list all jobs. Per job, use BQLS to list job information and get the required information. D. Use Cloud Audit Logging to view Cloud Audit Logs and create a filter on the query operation to get the required information. Okay, this is an auditing question. The goal is to get a reliable and accurate count of how many queries each user in a BigQuery project has run over the past month. We need to find the authoritative source for this kind of activity information in Google Cloud. With that in mind, let's look at our options. Let's start with option A, using Data Studio. This is incorrect because Data Studio is a tool for visualizing data, not for generating it. You would need to get the audit data from another source first before you could create a dashboard in Data Studio. Next, option B suggests querying the jobs table in BigQuery. While the information_schema contains information about recent jobs, it's not designed to be a complete, long-term audit log for all users. The official and most complete source of audit information is elsewhere. Option C, using the BQ command line tool to list all jobs, is also incorrect. This would be a very slow, manual, and inefficient way to try and count thousands or millions of queries. It's not a scalable or practical approach for auditing. This brings us to option D, which is the correct and Google-recommended solution. The definitive place to find this information is in Cloud Audit Logs. This service automatically records detailed information about activities across your entire Google Cloud project, including every BigQuery query that is executed. The logs include the user who initiated the job, the timestamp, and the query details. You can easily go into the Logs Explorer, create a filter to show only the BigQuery query operations for the last month, and then easily analyze that data to get the counts for each user. This is the most reliable and direct way to get the information needed for an audit. Therefore, the correct thing to do is D. Use Cloud Audit Logging to view Cloud Audit Logs, and create a filter on the query operation to get the required information. Question 203. For this question, refer to the Mount Kirk Games case study. Mount Kirk Games wants to migrate from their current analytics and statistics reporting model to one that meets their technical requirements on Google Cloud Platform. Which two steps should be part of their migration plan? Choose 2. Evaluate the impact of migrating their current batch ETL code to Cloud Dataflow. B. Write a schema migration plan to denormalize data for better performance in BigQuery. C. Draw an architecture diagram that shows how to move from a single MySQL database to a MySQL cluster. D. Load 10 terabytes of analytics data from a previous game into a Cloud SQL instance and run test queries against the full dataset to confirm that they complete successfully. E. Integrate Cloud Armor to defend against possible SQL injection attacks in analytics files uploaded to cloud storage. Okay, this question from the Mount Kirk Games case study is about planning the migration of their entire analytics system to Google Cloud. We need to identify 2 key planning steps that align with Google's best practices for building a modern data platform. With that in mind, let's look at our options. First, let's look at the incorrect options. Option C is about moving to a MySQL cluster, which is only a minor improvement and not the modern, scalable analytics solution that the case study implies they need. Option D is incorrect because Cloud SQL is not the right tool for a 10 terabyte analytics workload. BigQuery is. And option E is incorrect because Cloud Armor is a web security tool and is not relevant to a data analytics pipeline. This brings us to the two correct answers. Let's look at option A. This is a crucial step. They have existing batch ETL code. Part of any successful migration is to evaluate the impact of moving that code to a new platform like Cloud Dataflow. This helps them understand the effort and changes required. Option B is the other correct and critical planning step. Their old system likely uses a normalized relational database schema. BigQuery, the recommended data warehouse, performs best with a denormalized schema. Therefore, a key part of the migration plan must be to write a schema migration plan to denormalize the data. This ensures the data is structured optimally for performance and cost in the new environment. Therefore, the two steps that should be part of their migration plan are A and B. Question 204. For this question, refer to the Mount Kirk Games case study. You need to analyze and define the technical architecture for the compute workloads for your company, Mount Kirk Games. Considering the Mount Kirk Games business and technical requirements, what should you do? Create network load balancers. Use preemptible compute engine instances. B. Create network load balancers. Use non-preemptible compute engine instances. C. Create a global load balancer with managed instance groups and auto-scaling policies. Use preemptible compute engine instances. D. Create a global load balancer with managed instance groups and auto-scaling policies. Use non-preemptible compute engine instances. Okay, this question from the Mount Kirk Games case study asks us to design the main compute architecture for their new global game. The key requirements from the case study are that the solution must be able to scale to handle unpredictable traffic spikes and provide a good, low-latency experience for users around the world. With that in mind, let's evaluate our options. Let's first look at options A and B, which both suggest using a network load balancer. This is incorrect because the network load balancer is a regional service. For a global game with users in different continents, you need a global load balancer that can intelligently route players to the servers closest to them. Next, let's look at option C. This option correctly identifies the need for a global load balancer and auto-scaled managed instance groups. However, it suggests using preemptible VMs. This is a bad choice for a live, interactive game. Preemptible VMs can be shut down by Google at any time, which would disconnect players and create a very poor user experience. This brings us to option D, which is the correct answer. This describes the standard, best practice architecture for a scalable global application. You use a global load balancer to provide a single entry point and route traffic to the nearest region. You use managed instance groups with auto-scaling policies to automatically handle spikes in player traffic. And you use standard, non-preemptible instances to ensure the game servers are reliable and don't get shut down unexpectedly. Therefore, the correct architecture you should design is D. Create a global load balancer with managed instance groups and auto-scaling policies. Use non-preemptible compute engine instances. Question 205. For this question, refer to the Mount Kirk Games case study. Mount Kirk Games wants to design their solution for the future in order to take advantage of cloud and technology improvements as they become available. Which two steps should they take? Choose 2. Store as much analytics and game activity data as financially feasible today so it can be used to train machine learning models to predict user behavior in the future. B. Begin packaging their game backend artifacts in container images and running them on Google Kubernetes Engine to improve the ability to scale up or down based on game activity. C. Set up a CI/CD pipeline using Jenkins and Spinnaker to automate canary deployments and improve development velocity. D. Adopt a schema versioning tool to reduce downtime when adding new game features that require storing additional player data in the database. E. Implement a weekly rolling maintenance process for the Linux virtual machines so they can apply critical kernel patches and package updates and reduce the risk of zero-day vulnerabilities. Okay, this question from the Mount Kirk Games case study is about making strategic, forward-looking decisions. The goal is to choose 2 actions that will best prepare the company to take advantage of future improvements in cloud technology. With that in mind, let's evaluate our options. First, let's look at the options that are good current practices but less about future-proofing. Options C, D, and E: setting up a CI/CD pipeline, using a schema versioning tool, and implementing a patching process are all excellent things to do for operational stability right now. However, they are more about improving today's processes than making a fundamental architectural shift to prepare for the future. This brings us to the correct answers, which are more strategic. Let's look at option A. This suggests storing as much game activity data as possible now so it can be used to train future machine learning models. This is a key strategic decision. Without a large historical dataset, you cannot take advantage of future advancements in AI and machine learning to do things like predict user behavior. Collecting the data is the first and most important step. The other correct answer is option B. This suggests packaging the application in container images and running them on Google Kubernetes engine. This is another fundamental architectural shift that future-proofs the application. It makes the application portable, highly scalable, and less dependent on the underlying virtual machines. This positions the company perfectly to adopt new cloud-native technologies and deployment patterns as they emerge. Therefore, the two best steps to prepare for the future are A and B. Question 206. For this question, refer to the Mount Kirk Games case study. Mount Kirk Games wants you to design a way to test the analytics platform's resilience to changes in mobile network latency. What should you do? Deploy failure injection software to the game analytics platform that can inject additional latency to mobile client analytics traffic. B. Build a test client that can be run from a mobile phone emulator on a compute engine virtual machine and run multiple copies in Google Cloud Platform regions all over the world to generate realistic traffic. C. Add the ability to introduce a random amount of delay before beginning to process analytics files uploaded from mobile devices. D. Create an opt-in beta of the game that runs on players' mobile devices and collects response times from analytics endpoints running in Google Cloud Platform regions all over the world. Okay, this question from the Mount Kirk Games case study is about a specific type of testing called resiliency testing, which is often part of a chaos engineering practice. The goal is to actively test how your system behaves under bad conditions, specifically when there are delays in the mobile network. With that in mind, let's look at our options. Let's start by looking at option B, which suggests building a test client to generate realistic traffic. This is a form of load testing which is important, but it doesn't specifically test how your system handles network latency. It just sends normal traffic. Next, option C suggests adding a delay after the data has already arrived, before processing. This is incorrect because it injects the delay at the wrong point in the process. It doesn't test how the data ingestion part of your platform or the mobile client itself handles a slow network connection during the upload. Option D proposes creating a beta to measure real-world response times. This is a good way to gather data about your user experience, but it's a passive measurement. It's not an active, controlled test to see how your system breaks and recovers from specific failure conditions. This brings us to option A, which is the correct answer. This describes a classic chaos engineering experiment. You would deploy failure injection software to your analytics platform. This software is designed to intentionally and controllably inject additional latency into the incoming traffic from mobile clients. This allows you to safely simulate bad network conditions and observe how your entire system, from the client to the back end, behaves, which is the definition of testing for resilience. Therefore, the best way to test for resilience to network latency is deploy failure injection software to the game analytics platform that can inject additional latency to mobile client analytics traffic. Question 207. For this question, refer to the Mount Kirk Games case study. You need to analyze and define the technical architecture for the database workloads for your company, Mount Kirk Games. Considering the business and technical requirements, what should you do? A. Use Cloud SQL for time series data, and use Cloud Bigtable for historical data queries. B. Use Cloud SQL to replace MySQL, and use Cloud Spanner for historical data queries. C. Use Cloud Bigtable to replace MySQL, and use BigQuery for historical data queries. D. Use Cloud Bigtable for time series data, use Cloud Spanner for transactional data, and use BigQuery for historical data queries. Okay, this question from the Mount Kirk Games case study is about designing a complete database architecture. A modern, large-scale application like this has several different types of data workloads, and the best practice is to choose the right purpose-built database for each one, rather than trying to use a single database for everything. Based on the case study, we can identify three main types of data: real-time time series data from the game itself, transactional data for things like user accounts and leaderboards, and historical data for analytics. With that in mind, let's look at our options. Options A and B are incorrect because they suggest using Cloud SQL for either time series or historical queries. Cloud SQL is a great transactional database, but it's not designed for the massive scale of time series ingestion or historical analytics that this game requires. Option C is also incorrect. While it correctly identifies BigQuery for historical queries, it suggests using Cloud Bigtable to replace all of MySQL. Bigtable is a NoSQL database and cannot handle the strongly consistent, relational transactions needed for things like user accounts and leaderboards. This brings us to option D, which is the correct and recommended architecture. It perfectly maps each workload to the best tool for the job. You use Cloud Bigtable for its strength in handling high-volume, low-latency time series data. You use Cloud Spanner for its unique ability to provide globally scalable, strongly consistent transactions for the user accounts and leaderboards. And you use BigQuery as the data warehouse for running large-scale analytical queries on all the historical data. Therefore, the correct architecture is D. Use Cloud Bigtable for time series data, use Cloud Spanner for transactional data, and use BigQuery for historical data queries. Question 208. For this question, refer to the Mount Kirk Games case study. Which managed storage option meets Mount Kirk's technical requirement for storing game activity in a time series database service? A. Cloud Bigtable. B. Cloud Spanner. C. BigQuery. D. Cloud Data Store. Okay, this question from the Mount Kirk Games case study is asking us to choose the best database specifically for storing time series data from game activity. This type of data typically has a very high volume of writes and requires fast, low-latency access. With that in mind, let's look at our options. Let's start with the options that are not designed for this type of workload. Option C, BigQuery, is an analytical data warehouse, not a real-time database for serving an application. Option D, Cloud Data Store, is a document database best suited for application data like user profiles, not for the massive write throughput of a time series workload. Next, let's look at option B, Cloud Spanner. While Spanner is a very powerful database, it's a relational database designed for transactional workloads that need strong global consistency. It is not the specialized tool for handling time series data. This brings us to option A, which is the correct answer. Cloud Bigtable is Google's fully managed, wide-column NoSQL database. It is specifically designed and optimized for large-scale, high-throughput, low-latency workloads, with time series data being one of its primary use cases. It's the perfect choice for capturing and serving a massive stream of game activity data. Therefore, the managed storage option that meets the requirement is A. Cloud Bigtable. Question 209. For this question, refer to the Mount Kirk Games case study. You are in charge of the new game backend platform architecture. The game communicates with the backend over a REST API. You want to follow Google recommended practices. How should you design the backend? Create an instance template for the backend. For every region, deploy it on a multi-zone managed instance group. Use an L4 load balancer. B. Create an instance template for the backend. For every region, deploy it on a single zone managed instance group. Use an L4 load balancer. C. Create an instance template for the backend. For every region, deploy it on a multi-zone managed instance group. Use an L7 load balancer. D. Create an instance template for the backend. For every region, deploy it on a single zone managed instance group. Use an L7 load balancer. Okay, this question from the Mount Kirk Games case study asks us to design a resilient and scalable backend architecture. We need to choose the right kind of instance group for high availability and the right kind of load balancer for the application's traffic. With that in mind, let's look at our options. Let's first look at the options that suggest using a single zone managed instance group, which are B and D. These are incorrect because deploying your application to a single zone is not a highly available design. If that one zone were to have an outage, your entire application would go down. The best practice is to spread your instances across multiple zones within a region. Now let's compare the remaining options, A and C. Both correctly use a multi-zone managed instance group for high availability. The only difference is the type of load balancer, Layer 4 versus Layer 7. Option A suggests a Layer 4 or network load balancer. This is not the best choice because the application uses a REST API, which is based on HTTP. This brings us to option C, which is the correct and recommended architecture. It uses a multi-zone managed instance group to ensure the application is resilient to a single zone failure. And critically, it uses a Layer 7 or HTTPS load balancer. This type of load balancer is designed specifically for web traffic like a REST API. It understands HTTP requests and can provide more advanced routing features than a Layer 4 load balancer. Therefore, the best way to design the backend is C. Create an instance template for the backend. For every region, deploy it on a multi-zone managed instance group and use an L7 load balancer. Question 210. You need to optimize batch file transfers into cloud storage for Mount Kirk Games' new Google Cloud solution. The batch files contain game statistics that need to be staged in cloud storage and be processed by an extract transform load (ETL) tool. What should you do? Use SUDL to batch move files in sequence. B. Use SUDL to batch copy the files in parallel. C. Use SUDL to extract the files as the first part of ETL. D. Use SUDL to load the files as the last part of ETL. Okay, this question is about getting the best performance when uploading a large number of files to Google Cloud Storage. The keyword here is optimize, which means we want to make the transfer as fast as possible. With that in mind, let's evaluate our options. Let's first look at the options that misunderstand the role of SUDL, which are C and D. The SUDL tool is for copying files to and from cloud storage. It's not an ETL tool itself for extracting or loading data in that context. Next, let's look at option A. It suggests moving the files in sequence. This is incorrect for two reasons. First, a move isn't what's needed for staging the data. More importantly, performing the transfers one at a time or in sequence is the slowest possible way to upload many files. This brings us to option B, which is the correct and recommended practice. The SUDL tool has a powerful feature that allows it to perform operations in parallel, meaning it can upload many files at the same time using multiple threads. To get the maximum speed and optimize your transfer, you should perform a batch copy of all the files and ensure you are doing it in parallel. This will saturate your network connection and get the files uploaded much faster than a sequential copy. Therefore, the best thing to do is B. Use SUDL to batch copy the files in parallel.